So at this point, we've solved three partial differential equations involving the heat equation. Our first example was when we had a one-dimensional rod, a metal rod of length L, where we had an initial temperature distribution, and then we solved to see what would happen as time progresses and the heat diffuses throughout the material. So I typed in a rod length of 2 and an initial temperature distribution, which is the function equal to 1 if x is less than 1 and 0 otherwise. Then we've solved this problem, so I typed in our solution. Here are our coefficients times our exponential decay times the sine function. So I'm running this command. I've outputted the first 15 terms of the infinite sum, so I'll only get approximate answers, but it turns out that this is pretty good of an approximation. So here I have the first 15 terms in my actual solution to the heat equation. Here I've plotted what happens at time t equals 0. So the blue function is my initial temperature distribution in the rod. So the temperature is 1 degree here and 0 degrees elsewhere. Since I'm only using the first 15 terms, I get an approximation of the t equals 0 term with this Fourier sine series. Now I'm going to play the movie and it'll increase time. You could see that I'm holding the ends of the rod at a constant temperature of 0, and then the heat is slowly dissipating out the ends of the rod, cooling to an internal temperature of 0 throughout. That's if I hold the temperature at 0 on the sides. Next, we've solved the heat equation when we insulated both ends. So instead of holding the ends at a constant temperature of 0, the next problem we solved was when no heat can enter or escape outside the ends of the rod. So again, I started with the rod length of 2. I have the same initial temperature distribution, but this time I have a different, you can see last time I had a sine series. This time for the new problem, I have a cosine series, additionally with some extra constant term in front. So let me run this command. So here's my Fourier cosine series up until the first 15 terms. And that series at time 0 is the gold function, which approximates the blue initial temperature distribution. So again, this time I'm insulating the ends. Let's run time and see what the picture looks like. So now no heat can escape the rod. So no heat can escape out of the ends. So the internal temperature is just averaged. And I eventually get an internal temperature throughout of 0.5 degrees, which is clearly the average temperature of 1 and 0 on the interval from 0 to 2. The third problem that we solved involving the heat equation was the steady state two-dimensional heat equation. This is when we had a rectangular metal plate. We held 3 of the metal plate's sides at a temperature of 0 and let the top temperature vary. We waited a very long time until the changes in temperature settled down and looked at the internal temperature of the plate. So I've entered in our solution here. Here I took L to be 2 again and the height of the metal plate to be 1. I started with the same initial temperature distribution. This will be the temperature distribution on the top edge of the plate. And we found a solution in the previous video. This time I decided to go up to the first 50 terms. It involves hyperbolic sine, as you may have seen. And I have some constants in front. So here I'm going to enter my solution, and I'm also going to plot a picture of what the plate will look like after the steady state is reached. So I'm waiting for the machine to calculate. All right, so here are the first 50 terms in the series. I'm going to plot what the plate will look like after a while. So here, at the top of the plate, I have a temperature of 1 and then 0, and the other 3 sides of the plate are held at a constant temperature of 0. I waited a long time, and you could see how the heat is distributed internally in the plate after a while. So close to where the temperature is 1, I get, temperatures close to 1. And then far away, I get colder temperatures closer to 0. All right, excellent.